people here today. So I graded the exam 3, so you can take a look and look in your grades. I do want to go over one thing here. Let's see.
Professor,
Yes.
I have a question.
Okay.
So the homework grade is gonna change, right? Once we like complete everything that's due the 21st.
Right. Right. The homework grade should change. Right.
Okay.
But that's yeah. I mean, and if you want an extension, yeah, email me and I'll give you an extension. Okay. So let me talk about the exam, the 3rd exam. Okay. Probably the people who really need to hear this are the ones that are not here. Let's see. Here we go. All right. So here's the solution to the, I posted the solutions to the 3rd exam. Most people got the first one right, okay? There's some people that didn't understand, how to do this problem. They actually used the wrong form and somehow came up with the right answer, but I had to mark it wrong. So you have to use the right form. The form you have to use for solving this differential equation with the method of Frobenius, you have to use a constant times x, right, to the n minus r, right? You got to include that r, all right? The way some people did it, they didn't, a few people did it in a way that I didn't teach the class. And the way they did it, when you do something like this, you will get one solution, but you're not going to get the second solution. Okay, so this is the, these are the solutions. So once again, you can compare your solutions with my solutions. And if you think I made a mistake or I was unfair, we could definitely talk about it. Okay. I do want to, where most people messed up, it kind of really shocked me, was this problem here. Okay. And I knocked you off. If you got this wrong, I took off 7 points. I should have taken off 7 points if you got this wrong. And, you need to learn that a lot of people ended up getting exponentials as the solution. Okay. Now you need to, it's important to understand that when you get a solution, you should check your solution to see if it makes sense. And if you take a look at this differential equation, right, forget about Laplace transform. This differential equation is telling me that my general solution is going to be sines and cosines, right? Because this is going to be, this is m squared, right, plus 64, right? And so that's going to become m plus or minus I times 8, right? So I'm going to end up getting sines and cosines as the general solution. And a lot of people ended up coming up with, I think it was about 6 people in the class came up with the same solution, but they came up with exponentials. And you should realize that that it can't be exponentials. Okay, so I was really surprised. I thought this problem was an absolute giveaway. I thought that this problem, everyone would get it right. By the way, I think there was 500s in the class. So that's really good, 500s.
Professor?
Yes.
Sorry, for the last problem, can you explain how you get divided by 8? Where that comes from?
Yeah, okay, we have this 10 here, right?
Right.
Okay. This is the form for the inverse Laplace transform.
Okay.
Here, I need 8 here. So I put an 8 here and another 8 down here.
Okay, that makes sense.
Right?
Yes.
Okay. Now, most people had this solution here, and if you had 4, whatever. Okay. All right. So once again, compare your answers with my answers, and I'll be happy to, to discuss your results with you. Okay. So now we're going to do our last topic. Okay, so well, let me tell you too about the schedule between now. So today we're going to do the last topic, and I find that students in the past have gotten this right on the exam. So we're going to look at a system of differential equations. Let's see. So we'll have a short class tomorrow, right? And tomorrow you'll download exam 4. And then I'll have a little bit of a review on Wednesday, and that could be as long as you want it to be. And then we'll have the final exam on Thursday. There'll be no class on Thursday, okay? So on Thursday, I'll let you be able to download the final exams starting at 8:30 in the morning. So at 8:30 in the morning on Thursday, you can download the final exam, and I'm giving you plenty of time to, I'm giving you plenty of time to do all the exams, okay? Now, the other thing too is that this weekend I posted where you presently are with your WebAssign grades, and there's a few students that that kind of like have an A average, and the WebAssign grade is actually right now is going to bring them down possibly to a B. And the same is true. There's a few students with B averages that their WebAssign grade is going to end up bringing them down to maybe a C. So, try to get that done. And, I actually do the harder problems are in my notes on the WebAssign. There's a lot of problems where you just have to do different numbers. So there's really, and I've talked about the WebAssign as being, 15% of your grade at the beginning of the year. And it's in the syllabus. So I'm hoping that people don't fall down because of the WebAssign grade, but it looks like a couple of people may. There's actually one this has never happened. Okay, there's actually one person that has 100 right now on the WebAssign grade, and I think one person has a 99.3. I never seen WebAssign grades that high, so I'm not going to embarrass anybody, but those two people, I should put my video on. Those two people deserve a lot of credit. Okay, let me put my video on. Okay. All right. So any questions right now? So I'm going to start on systems of differential equations. I think you'll find this topic pretty straightforward. So now let me stop recording. Okay. All right. So systems of differential equations. And so I'm going to be using my notes. So you can follow along on my notes if you want. But let's see. I'll be writing stuff down. I know everybody likes it better if I write it down. So you will have one problem on the exam where you have to solve a system of differential equations. Now, some of the things that I'm going to talk about today, maybe you learned about in high school, like what a matrix is. And okay. Now, normally we write this in bold. I can't write this in bold, but we have a matrix A, right? And a vector that, and then we have this lambda and another vector. This is what we call an eigenvalue equation, right? This is an eigenvalue equation. And to solve a differential equation, what we're going to have to do, we're going to have to find the eigenvalues. Okay, so that's the first thing. Okay, how do we find the eigenvalues and how do we find the eigenvectors? And once we know how to find the eigenvalues and eigenvectors, that's basically the solution to a system of differential equations. Now we're only going to deal with 2 by 2. Okay, we're only going to deal with a system of differential equations that. Because it's easy to expand. Let's see what I do with this top sheet. Yeah. We're only going to deal with a system of differential equations that look like this. Okay. Now, if you had if it was we had z in another term, it's not any different. You're just going to have a 3 by 3 matrix, and it's going to be a little bit harder to evaluate the eigenvalues in the past, we've, you can use MATLAB to get the eigenvalues if you have higher order dimensions. Okay, so this is a matrix, right? This is a vector. You can look at my notes. This is our eigenvector, and this is the eigenvector. Okay, this is the eigenvalue. This is the eigenvector. All right. So the first thing we need to know is, well, I also have here on my notes that I got this eigenvalue equation. So let me talk about this for a minute. It should be about learning. This eigenvalue equation, you remember in chemistry, you learn about the principal quantum numbers like n, right? And the fact that, so these are the people taking chemistry. The n can, L, the quantum number L goes from n to -1. And then you have the magnetic quantum number that goes from -L to +L, right? If you've taken a course in chemistry, you're aware of this. All that stuff comes from this differential equation here, which is actually an eigenvalue differential equation. And the energy, the angular momentum, those are eigenvalues, okay? They come from this differential equation, and the energy levels of the eigenvalues. These values here, N and L, and these come from separation constants. When you solve a partial differential equation, you have to separate it, and you get these separation constants. So it's kind of really cool how the mathematics, the physics, and the chemistry kind of all work together. But you're not responsible for this. I just want to mention that. If any student has had chemistry. Okay. All right. So first of all, how do we find the eigenvalues? Well, we find the eigenvalues. We take the determinant, okay, of the matrix minus the identity matrix, right? And we set that equal to 0. That's how we find the eigenvalues. Now, the identity matrix, very simply is just, because if I multiply any matrix times the identity matrix, I'm going to get the matrix back. Now, do you know how to multiply matrices? Let me just on the side here. It's actually on the next one. Let's say that that we have say we want to multiply these two matrices. Well, just as a review, maybe you've seen this in high school. It's this times this and this times this gives me this element. So this element here is be 1, 1, K1 plus 1, 2, K2. And then this here is going to be this times this and this times this. So this is going to be A1, K1 plus A2, 3, K3. Right? So you end up getting, so that's it. Okay, so let me give you an example. So let's say I have this matrix here, and I want to multiply it by this, right? Let's see. This times this is 4. This times this is 3. So this is going to give me, so that's going to be 7, right? 4 plus 3 is 7. This times this is 2, right? This times this, and these are to make, this is what you're going to multiply. We're going to be multiplying 2 by 2 and 1 by 2. Okay. So so this would be 2. This is going to be 4, and then 1. So this is 5. Okay. So that's how you multiply these two matrices. Okay. And these are that's what you need to multiply for the type of problems we're going to be doing. Okay, so all right, so how do we find the eigenvalues? Well, I guess I could write it out, but basically it's the determinant of A minus lambda times the identity matrix. So if I write this out, I might have left this step out in my notes. So let's say the matrix is it's going to be the determinant of A. Let me make my matrix A let me do this. Let's say A, I'll use what's in my notes is 2, 3, 2, 1, okay? And, okay, so what is A minus lambda? This is not my notebook. I want to make this clear. What is A minus the identity matrix? Well, if I write this as, so write this as 2, and then 3, and then 2, and then 1, and then minus, it'll be the identity matrix, which would give me a lambda here, 0, 0, and the lambda here, right? Remember now, this is the identity matrix. So now I have lambda times the identity matrix. So that makes this a lambda. This is a 0. So what do we end up getting here? We get 2 minus lambda, 3, and then we get 2, right? When I subtract these two, and then I get 1 minus lambda, okay? And if we take the determinant of this, right? That's how we're going to calculate the eigenvalues. All right. So let's see. So let's see. So let's calculate the eigenvalues of this. Okay. So now I'm going to take the determinant, right? It's going to be this times this, right? So I'm going to have 2 minus lambda, and then 1 minus lambda, and then this times this is going to be a minus 6, right? Okay, so let's see. So what do I get here? I get 2. This time this is 2. This time this is minus 2 lambda. This time this is minus lambda. This time this is plus lambda squared minus 6. So let's see. I'm getting here lambda squared minus 3 lambda, right? Minus 4 is equal to 0. Right? Did I do that right? Okay. All right. So okay, so I could factor this now, right? I could factor this into this could be factored into lambda minus 1 and lambda minus plus 4. Hold on a second. So I'm mistaken my notes. Well, this is plus 1, and this is minus 4. Right? So that's giving me the middle term, right? That's giving me the middle term of minus 3. So my eigenvalues are lambda 1, I'm going to call it lambda 1 is equal to minus 1, and lambda 2 is equal to 4, right? So those are my eigenvalues for this matrix here, right? Those are the eigenvalues for this matrix here. Okay. Let me see. I guess before I go on, why don't you, just to make sure, this one is not in my notes, but see if you can do the eigenvalues. Make this too. Find the eigenvalues for this matrix. Okay, for this matrix A, find the eigenvalues. Okay, before I go on. I'll give you another minute. All right, so let me do this. So we want to find the eigenvalues of this matrix. So I'm going to write this as 0 minus lambda. You don't have to go through that. Just whatever you have here, put a minus lambda, right? Whatever in this position here. And then you can write this as 1 minus 2. Then you have a minus 3 minus lambda, right? Then I'm going to take the determinant of this, right? You take the determinant of this. So this times this, right, is going to be, let me do it this way. Don't have to worry about the 0. So this time this is minus lambda, right? And then I get a minus 3 minus lambda. And then this times this time this is minus 2, but when we cross this way, this is plus 2. Right? When we take the determinant, this is, we have to have this as a minus. So this time makes this a plus. All right. So let's see. So what do we get here now? I get, let's see, I'm going to get 3 lambda, right? The minus lambda times the minus 3, that's going to give me 3 lambda. And then I'm going to get a plus, also a plus lambda squared plus 2 is equal to 0. So I'm getting now that lambda squared plus 3 lambda plus 2 is equal to 0. So let's see. So I can factor this. I can factor this into lambda, lambda plus 1, right? And lambda plus 2, right? So I get now that lambda is equal to minus 1 lambda. And you want to label, because we have to find the eigenvectors. And we want to find the eigenvectors for each value of lambda, right? So it doesn't matter, but label one of them lambda 1, and the other one will label lambda 2, right? So these are the 2 eigenvalues, okay? These are the 2 eigenvalues for this matrix, right? We got the 2 eigenvalues for this matrix. Okay. So now we want to learn how to find the eigenvectors. And basically, once you have the eigenvalues and eigenvectors, then you can write the solution to a system of differential equations. We'll see how that works. Okay, so let me take a look. So now we need to, oh, before I do that, notice that that my eigenvectors here, right? Excuse me, these are the eigenvalues. My eigenvalues here turned out to be distinct and real, right? So just like when we're solving, you know, second order differential equations, we sometimes got distinct roots, right? We use the quadratic equation, and we got distinct roots, we got repeated roots, and we got complex conjugate roots. Remember that? Okay, hopefully. So here too, when we have distinct eigenvalues, right, and they're real, we're going to end up, the solution to our differential equations are going to end up being, the solution to our system of differential equations are going to end up being exponentials. If the roots turn out to be repeated roots, well, you're also going to get exponentials, but you're going to get an exponential times, you know, additional factors that we have to do, just like we did with when we did second order linear differential equations with constant coefficients, right? And then if you have complex conjugate eigenvalues, in other words, these eigenvalues are complex conjugates, then you get sines and cosines, all right? Now, in this class, we're only responsible for the real, okay? So, you know, this is what's in my notes. So the eigenvalues can be distinct and real, right? They can be complex conjugates, and they can be repeated and real. So there are three different cases, right? So we'll only consider the case where the eigenvalues are real. And it's easy to go to the next step, but we're not required to do that. Where you get sines and cosines and how to deal with when you have repeated roots. Okay. All right. So we're only going to deal with distinct real eigenvalues. But be aware that if you have the you're going to get sines and cosines in some cases. All right. So now what? All right. So now we have to. So we know how to find the eigenvectors, right? Everybody knows how to find the Everybody knows how to find the eigenvalues. So now we have to learn how to find the eigenvectors. Okay. Now, a mistake that's commonly made, and I've made this mistake, is make sure you associate the right eigenvalue with the right eigenvector. So in other words, now remember that our eigenvalue equation looks like this. It's a matrix, and this is the way I like to do it. It's a matrix, and then it's times a vector, and then you got the eigenvalue times the vector again, right? So that's the equation we want to solve, right? That's what we want to solve. Now, the notation I use is actually different in the book. I think your book is very confusing. All right. So now, let's see. See, this turned out to be. Got to make sure I do the same problem. Okay. So here's our matrix, right? Our matrix is 2, 3, 2, 1. Okay, that's our matrix. Now I want to find the eigenvectors. All right. So so what has to happen now? Well, let's say I want to find V1, right? In other words, I'm going to have an eigenvector. Let me do this. I'm going to have an eigenvector associated with eigenvalue 1, and I'm going to have an eigenvector associated with the eigenvalue 2, right? So make sure you don't mix these up, right? You won't get the right solution. You won't get the right solution to our differential equation if we have the eigenvalue 1 with the vector 2 when we actually write out the solution. All right. So how do we find V1? Right? Well, here's the equation, right? And this is the way I like to do it. Now this is the vector I don't know, so I'm just going to call it K1 and K2. I don't know what it is. And then right, the vector is the same on both sides. This is the way I like to do it. All right, so now let's see. So we found that, what did we find? We found that lambda 1, where we find lambda 1 was. We found that lambda 1 was -1 and lambda 2 was 4. Okay. All right. So now I want to find this is 1 here. Okay. So let's see. So now I want to find V1. All right. So what I'm going to do here, I'm going to do 2 and then 3 and then 2 and 1. I'm just copy this over. And then I'm going to write this is K1, K2, just copy this over. And here now I'm going to put in -1. Okay. Now what's going on here? So row by row, they have to be equal. So in other words, 2 times K1, right? 2 times K1, 2 times K1 plus 3 times K2 has to be equal to minus K2. All right. So let's see. Let's and so I bring this over. Yes.
On the right, are those both K2 in the
Oh.
matrix?
Thank you. Yeah, this should be 1.
Yeah, just
Yeah. Right. Okay, good. All right, so, yeah, I would have found my error now, I guess. This would have been. Yeah. I normally find my error, but thank you. Okay, so,
Professor,
yes,
shouldn't the lambda next to the first vector equation be a 4? Or is there a reason why you left it a lambda?
no, well, I'm associating this with lambda 1, right?
Uh,
So lambda 1 is -1. Lambda 2 is 4. I have to do both.
right.
I have to get vector 1 and I'm also gonna have to get vector 2 using 4.
Right. But in the second eigenvector equation, you wrote out. Oh wait, that's just the general method, right? Okay. I think
You think you got it?
I got it now. Thank you. Sorry.
Okay. All right, so so what am I getting here now? I'm getting here that let's see. When I bring this over to here, I'm getting minus, yeah, I'm getting well, I can write it like this. There's different ways of writing this. This is gonna be when I bring this over to here, there's gonna be minus 3k. I think in my notes, I think I wrote it differently in my notes, but anyway, it doesn't matter. So this is what this is telling me is that K2 is going to be equal to minus K1, right? Now the second equation is going to turn out to be, it's going to give me the same thing. You only have to do the first, okay? But if we were to do the second, let's see. If we were to do the second, let me do the second just to show you. This is going to be a K, right? And then I'm going to get a plus 1K, right? This times this and this times this, and that has to be equal to minus K2, right? So so I bring this is K1. This is the K1. Yeah, okay. So when I bring this over to here, once again, I'm getting that 2K1 is equal to, bring this over to here, it's minus 2K2. So once again, I'm getting that K1 and K2 are, well, here I'm getting K1 is equal to minus K2. But the same thing, right? Okay, so you only need to do one of them, all right? Now, here's the thing is that it's not unique, okay? I have to have, in other words, for my vector V1, I have to have the K1 is the K2 is the negative K1. So if I set K1 equal to 1, right? If I set K1 equal to 1, then K2 is equal to minus 1, right? Now I could set K, in other words, it's going to turn out that any constant times this will actually work. And the reason for that is that we're going to end up finding the general solutions to the differential equation. If I was given the initial conditions, right, that would tell us exactly what the values would have to be. All right, so I want you to understand that it's somewhat arbitrary. And normally the easiest way to do it is choose K1 to be 1, okay, and then figure out what K2 would be. All right. Now, there's also sometimes, maybe I shouldn't get into this, it'd be more confusing. You can actually also normalize this, all right? But it's not necessary, all right? So I do want you to understand that, you know, I chose K1 to be 1 and K2 to be minus 1, but actually it's any constant would work, all right? Any constant would work. In other words, V1 can also be 2 and minus 2, right? It could be 3 and minus 3. It can't be 1 and 4, okay? You know, it can't be anything you want it to be, but it could be any constant times the 1 times the minus 1. Okay, so All right, so let's see. All right, so V1, we said is going to be 1 minus 1, right? That's what we said V1 is going to be 1 minus 1. So let's figure out what V2 is, right? So V2, to get V2, let's see, my other eigenvalue was 4, was minus 1 and 4, right? The other eigenvalue was 4. All right, so the other eigenvalue is 4. Let's see, so now, let's see, I'll just do the top one. So I get 2k1 plus 3k2 is equal to 4k1. Okay, so let's see. So what do I get here now? I get, I can write this as 3k2 is equal to, let's see, 3k2 is equal to 2k1. Want to do the, right? Bring this over here. Okay, so now, let's see. If I set, I'll do what I did in my notes. In this case here, I set K1 equal to 3. If I set K1 equal to 3, yeah, if I set K1 equal to 3, then K2 is equal to 2. Once again, it's arbitrary. I could set, I want to deal with integers. That's why I'm setting this equal to 3. If I set this equal to 3, right, then I get 6 on this side, and this equal to 2. If I set this equal to 1, I could do that, but then I'm going to get a fraction here. All right. Once again, it's arbitrary, but that wouldn't be wrong to do it that way. All right. So so once again, now this is the eigenvector that's associated with the eigenvalue, what was it, minus 1, right? And then the eigenvector 2 that's associated with is going to be 3, be 3, 2, right? And that's the and that eigenvector is associated with the eigenvalue 4. Okay. All right, I want you to try to do something now. Let's see, where's the let's see. I just had you try to find the eigenvectors of this problem here, right? Copy this over again. And when you found the, find the eigenvalues, you found the eigenvalues of this, right? What did they turn out to be? The eigenvalues turned out to be -1 and -2. All right. I want you to try to find out the eigenvectors. Try to find the eigenvectors associated with these eigenvalues. Okay, for this matrix. And then I'll do it. Be back in a second. Okay, so let me give you a couple of minutes to try to do that. Get the eigenvectors associated with these eigenvalues. Okay. So hopefully everybody's getting this. Be another minute. Let's see where we are. On time. All right, so let's see. Let's go ahead and find the eigenvectors for this matrix, right? And so let's find V1, right? So V1, I have to make sure that I associate V1 with lambda 1. We'll see why that's important in a minute when we solve the differential equation. So let's see. So this is I'm gonna write this as 0, 1, -2, 3, and then I'm gonna write K1, K2, minus, I'll put in the -1, and then this K1 plus K2. So let's see. So this is 0, right? This times this is 0. This times this is going to be K2. Then I'm going to get minus this times this. Yeah, this times this is going to be minus K1. And then I'm going to get a minus K2. So I'm getting this isn't something's not right here. Okay. This is K1. This is K2. And this is just K1. What am I doing? Okay. So I'm getting a K2 is equal to minus K1, right? So if I let K1 equal to 1, then K2 is equal to -1. So
Professor,
yes,
the 3, isn't it supposed to be -3?
yes,
Inside the
it
sentence?
is. You're right, but it doesn't matter. I'm just using the top line, right? That's right. That should be a -3. If I use the bottom line, I better get the same. I better get an equivalent equation, right? I'm using the top. Okay. Okay. All right. So let's see. So So I got that if I set K1 equal to 1, then K2 is equal to -1. So my vector V1 is going to be 1 minus 1. So that's my vector. Did everybody get 1 minus 1 or some constant? You know, if you got 2 minus 2, that would be the same, right? But the thing is, you have to have that the K1 is the negative of K2. Okay. It would also be correct to multiply. It would also be correct to have this is -1 and this is 1. Okay. That would also be correct because I can multiply this by -1 and would, okay. And we're going to see that, you know, it's actually, when we write this V1, we can actually write the V1 times any constant. Okay. All right. So that's the V1 that's associated with the lambda 1. So let's see, let me copy the matrix again. This would be 0, 1, -2, -3. Now I have K1, K2, and let's see, what was the other eigenvalue was -2. Right, the other eigenvalue was -2. So this is going to be 0, and then I'm going to have K2, and then this is going to be 2, K1, right? And you will get an equivalent equation if you use the bottom, all right? But let's just use the top. So let's see. So if I let K1 equal 1, then K2 is going to be equal to -2, right? So my vector 2 is going to be equal to 1 minus 2. So this is the vector 2 that's associated with lambda 2, right? Which was -2. Okay. Any questions? Let me just something that's in my notes. I don't want to necessarily go through this, but you can see that here's a check, right? This is the problem that it's in my notes where you know, this is what I found, right? We found, before I let you do it, we found this is the eigenvector. We found that lambda 1, right? For this matrix, we found that lambda 1 was equal to -1. And we found that lambda 2 was equal to 4. And then this was the eigenvector associated with lambda 1. And then this is the eigenvector associated with lambda 2. That I could check this, right? That if I put in this eigenvector, right, and this eigenvalue, and work out the matrix, you can see that you know, when we multiply this out, right, we do get the eigenvector on both sides of the equation, the same eigenvector on both sides of the equation, right? Does everybody see this? Pretty straightforward, right? When you multiply this times this, you're going to get 2, right? And then this times this is going to be -3, so that's the -1, right? That's the -1 here. Okay, and the same thing here too, that if I use this eigenvector, right? Yeah, if I use this eigenvector V2 and this eigenvalue, show you that it does satisfy the eigenvector equation. All right, so that's all we're doing here, is showing you it's a check that that we did solve this eigenvalue equation, and that the eigenvectors and the eigenvalues, you know, we get identity on both sides of the equation. Okay. Now what's next? Okay, now how do we use this to find a system of differential equations? Okay, I'll write this out, but first let's take a look at my notes. So we have a system of differential equations, right? And so here I got these coefficients A, B, C, and D, right? Right. If I write it like this instead, right? If I have the system, I write it like this, then I can put this in matrix form. That's all I'm doing. I'm taking my differential equation and putting it in matrix form. All right. So you see, the x dot times the a, and then the x dot times a times x1 and b times x2 is equal to the x1 dot, right? And let's see, and c x dot 2 is equal to c times x1 times d times x2. All right. So so I have this system of differential equations. I could write it like this, and now I have this system written in terms of the matrix. Now, so this is in terms of matrix equation. So this, I can write this now. Okay, I can write it like this, but then I can also write it using you specifying that this is a matrix, right? That's what when we write this as a capital dot, we mean that this is a matrix. So this big X with a dot over it corresponds to this column matrix, right? The A here corresponds to this matrix here, and the X here corresponds to this. So this is the derivative, right? All right. So just like we did with second order differential equation with constant coefficients, we assume a solution of this form, right? I assume a solution of this form. When I take the derivative of this, look what happens. When I take the derivative of this, right? This just is going to bring down a lambda, right? That's all it's going to do is bring down a lambda, right? When I take the derivative of this. Okay. So, all right. But the derivative is equal to this. It's also equal to this. Okay. So let's see. Right. So I take the derivative of this, right? And the x dot, right? The x dot is equal to this. So I now end up with this. I hope you see that. I end up with this. Okay, and what happens is that these things cancel out, right? These things cancel out, and so I wrote it differently. So now I have this, right? But I can rewrite it like this. I just put it on the opposite side. So now I got my eigenvalues. So in other words, to solve a system of differential equations, we just need to put it in matrix form, find the eigenvalues and eigenvectors, and that's going to give me the solution. Let's see. Anything else I want to say? Okay. See, x, does anyone have any questions? X dot is equal to this. I put this over here. And then x is equal to that. Okay, maybe I should write it out. So you see what's going on. X dot is equal to AX, right? Okay, so and we know that X is equal to V e to the lambda, right? Now, now X dot, right? Take the, I assume a solution of this form. I'm assuming a solution of this form. So this is going to bring down the lambda. Right. Okay. So now I get this, right? I take this here and put it here. But X is equal to this. So this cancels with this cancels. Maybe that's a little clearer. Okay, and then you just can reverse this. All right. So, okay, if you understand this, great. But once, like I said, once we have the eigenvectors and eigenvalues, then we have the solution to the differential equation. So here's what we did, right? We had, well, let's say we have this system, right? Okay, so I could write it like this. Right, and this is the matrix we just solved. This is the problem we just solved. So what I'm telling you now is that we actually have the solution to this system of differential equations, because it corresponds to this matrix here, which is the matrix that I've been working with, right? And we found that the eigenvalue, right? We found that the eigenvalues for this matrix was lambda 1 was equal to -1 and lambda 2 was equal to 4, right? And that we found that these were the eigenvectors, right? So in other words, I can write the solution to the differential equation like this, right? Where C1, that's why I said that C1 is any constant, right? C1 is a constant. Now C1 and C2 will be determined by the initial conditions. And I'm not going to give you any problems with the initial conditions, but C1 and C2 will be determined by the initial conditions. So I could write it like this. This is the solution in matrix form. This is the solution to the differential equation in matrix form. Okay, so it's just now see the eigenvalue. Well, understand that the eigenvalue is what's in the exponential, right? Because we're showing, I'm proving to you here that we're assuming a solution of the form e to the lambda t, right? So lambda t is our eigenvalues. I mean, lambda is our eigenvalues, right? So so in this case here, where the lambda 1 was -1, lambda 2 was -4. See, here I got a -1, and here I got, +4, and here I got a +4, right? So this is my solution to my differential equation. Now let's see. This next just shows that, so as far as I'm concerned on an exam, you're going to get a problem just like this, okay? The next exam's going to have a problem just like this. The only thing, the numbers are going to be different. So if you follow what I'm doing here, you have no problem with, and I found in the past that students always got this problem right. So the only thing is going to be different numbers. So hopefully everybody's going to get this problem right on the next exam. All right, so so this is our problem. This is the matrix that we worked with, right? And we found the eigenvalues and eigenvectors. I just want to show you different ways of writing it, right? I can write it like this, right? Where this is, I put in what the eigenvalues are here, the -1 and the 4, and then this is my eigenvector. See, if I had the eigenvector here with this, it would be wrong, right? That's why it's important that when you find the eigenvalue, you associate the right eigenvector. In other words, if this was written, if I put the V2 here and the V1 here, it'd be wrong, okay? It wouldn't satisfy the system of differential equations, all right? So this is one way of writing out the solution. And if you write out the solution like this on the exam, I'm perfectly happy. Another way to write out the solution is like this. I can write it out where C1, right? In other words, all I'm doing here is I'm putting in that this is X1 and this is X2, right? This is X1 and this is X2. I'm calling the Y X2 now, all right? And then this is my eigenvector, right? The 1 and the -1. And then this is my other eigenvector, 3 and the 2. And then I got these constants, C1 and C2, all right? And then this is multiplied by e to the -t, and this is multiplied by e to the 4t, right? So another way of writing it out too, I'm just showing you different ways of writing out the answer. I can write out the answer like this, right? Where it's this, x1, c1, e to the -t, c2, 3 e to the minus. Write it out like that, right? And write it out like that. So this is just different ways of writing it. Now, the way your book writes it, they write it like this, and but it's equivalent. In other words, now, if I want to go back to X and Y, I can write this as a vector, okay? And this is telling me that X is a function of T and Y is a function of T. So now I'm going back to the X and Y, and then my C1. And now when I write this in terms of a row vector instead of a column vector. These are column vectors, right? So this should be C1, right? Is equal to, so I hope everybody sees this is just 1 minus 1. And then once again, you have the e to the -t, and then the C2, and then this is 3 times 2. So any one of these as the final solution to the differential equation is good with me. Okay. Okay, let's see how we're doing on time. Okay, so over here, you could just, you could check. In other words, let's see. So if I have this system of differential equations, right? I could check and see if I satisfy, it. And it turns out it does. That's all I did here was check that this system satisfies this system of differential equations. Okay, so I want you to try. Okay. I want to give you a couple of minutes to try a problem. Like I said, you can have a problem just like this. Okay. All right. So try to solve the system of differential equations. Now, let me just start you out. The first thing you're going to do is write this matrix is going to be. Make sure I copied it right. Right. And then you're going to find the eigenvalues and eigenvectors. And then once you find the eigenvalues and eigenvectors, you assemble it the way I showed you to find the system of differential equations. All right. So see if you can come up. So on the exam, you have a problem just like this. Different numbers. You're gonna have to find the eigenvalues. You're gonna have to find the eigenvectors, and then you're gonna have to write out the solution. Let me just go back to here. And then you're gonna have to write this. Once you have the eigenvectors and eigenvalues, then you're gonna have to write out the solution in any one of these forms. Right? You can write it out like this, write it out like this, you can write it out like this, you can write it out like this. Okay, so why don't you try to do that problem, and then you'll get this problem right on the exam, on the fourth exam. And this is also a WebAssign problem. So, so you do have a WebAssign problem. I think it's the last problem I gave you, the WebAssign, where, but you're going to have different numbers. So I do want you to try to do the WebAssign problem. So let me give you some time to work this. My plan is to have a really short class tomorrow, unless there are questions. And then on Wednesday, I'll talk about the final. And then there's, I'm not planning on to have any class on Thursday. On Thursday, you'll have all day to work on the final if you want. And I'll make the final available like at 8:30 in the morning. So and the final is probably, it's not much longer than the other exams. Well, maybe it's a little bit longer. I think exam 2 was probably the longest. minus 32 is equal to 0. Okay. Let's see. So this is going to give me 21. This time this is 20. The middle term is going to give me a 10, right? That's going to be a minus 10 lambda, right? This times this is 3. This times this. And then I'm going to get a plus lambda squared minus 32 is equal to 0. Okay, so here I'm going to get, so let me write like this, lambda squared minus 10 lambda minus 11 is equal to 0. Okay, so I think we can factor this into lambda. It looks like lambda plus 1 and lambda minus 11, right? That's going to give me the middle term of minus 10, right? So then lambda is equal to minus 1, and lambda, or the eigenvalues, is equal to plus 11. Okay. All right. So so I'm going to call lambda 1 11. I'll call this 1, call this 2, only because that's the way I have it in my notes. I could call that, I could call this 1 and this 2. It doesn't matter. You just have to make sure that you associate the right vector. Okay. So, all right. So now I'm going to find so here's 11. So let's see. So this times this, I'm getting 3k1 plus 4k2 is equal to 11k1. All right. So let's see. So let's see. So this, I can write this as 8. Let's see. This would be minus. If I bring this over to here. I can write this as minus k1 plus 4k2 is equal to 0. Right? If I bring the minus 11k1 over here, I'm getting the minus 8k here. So now I'm going to set k1. I always like to set k1 equals to 1. Set k1 equals to 1. So I set k1 equals to 1, right? Everybody can see the k2 for this equals to 0. K2 has to be equal to 2, right? So my eigenvector, v1, I can write as 1 over 2, right? I can write it like that, or we can also write it like this. There's notation your book uses, right? I can write it as a column vector. I can write it as a row vector. So when I write it as a row vector, put these symbols like this. Okay. If you're taking calculus 3, sometimes you write vectors like this. Okay. But sometimes in linear algebra, you write them like this. Okay. All right. So so that's my, I wish I did it all on one page. So now let me find, let's see, let me find now, this will be minus 1, right? Let's see. So now I got the same thing, 3, 4, 8, 7. And this is K1, K2. And this is minus 1. And then this is K1, K2. All right. So I'm getting 3K1 plus the 3K1 plus 4K2 is equal to minus K1, right? Okay, so this is telling me that if I bring this over to here, right, I could write this as 4K1 plus 4K2 is equal to 0. right? So if I set K1, right? If I set K1, I set K1 equal to 1, then K2 is equal to minus 1, right? I can actually do it the opposite way too. I can set K2, yeah. All right, so my vector V2, is I could write it as 1 minus 1, or I can write it as 1 minus 1. Okay. All right, so now we put it all together. So I can write the solution, right? I can write the solution to the differential equation. I can write it like, let's see. Well, let me write it first. I can write it as x1. There's different ways of writing it. X1, x. This is a vector now, all right? C1, and then this would be 1 over 2, and then it'd be E. What was the eigen? This was minus 1, right? This is got to make sure. 1, 2, it's 11. Oh yeah, we did the 11. So this is 11t, right? I called lambda 1 11. All right, I called lambda 1 11. So that's that, and then plus C2. C2 would be 1 minus 1, and then E. In this case, E was lambda 2 was minus, right? Minus 2. So that's one way of writing it. Okay. Another way of writing it would be x1 is equal to C1 E to the 11t plus C2 E to the minus t, and then I can write x2 is equal to C1 2 E to the 11t minus C1 E to the minus t. All right, it's another way of writing it. And finally, another way of writing it, I can write it like this too. This would be C1, and then be 1 comma 2 E to the 11t plus C2 1 comma minus 2 E to the minus t. So these are different ways of writing it. So you're going to get a problem just like this. I just want to show you something else, and we're done for the day, I guess, unless anybody has questions. But so here's the solution. Here's the WebAssign solution, right? And this is the solution I came up with. And notice that here we got the minus 1 and the 1. Here's the 1 and the minus 1. But don't forget, the reason why both of these are correct, and the WebAssign will accept either answer, right, is that because we got the constant C1 and C2, right? And these constants will be determined by the initial condition. Now, I'm not giving you the problem we have to do the initial conditions. Maybe I should have done. Okay. So, but I wanted to show you here that in this case here, if I chose K1 to be minus 1, which I could, and chose K2 to be if I chose K1 to be minus 1, or then K2 would be plus 1, and then I would get this. Okay. And here, what I did here is I actually did the top and the bottom just to show you get the same equation, right? In other words, what I did here in my notes is I did the 3K times the 4K is equal to the 11K1, right? The 3K1 plus the 4K2 is equal to 11K1. Then I also used the bottom and showed you here that you end up with the same equation, right? This equation is equal to this equation. This is just, just -1 times the other. So these two equations are equivalent. The same thing here, just to show you that if you use the top and the bottom, you're going to get two equations that are equivalent. This equation is equivalent to this equation. Okay. So it's always easier just to use the top. Okay, so this is our last topic. Does anyone have any questions? I thought it was going to take me longer to do this. Do the problem. So this is pretty straightforward, am I right? You find the eigenvalues, you find the eigenvectors, and then you assemble a solution. Okay, and the reason why this works is because right here, I mean, we're assuming that this is a solution, and in my notes too, I just checked. In other words, we found the solution. We found the solution. Here's the solution. I took the derivative and plugged it into the differential equation, and it does satisfy. It checks. See here, we get both sides equal. Okay. So the method works, and if you went to if you had a system of differential equations where, say, you had a z, then you'd be doing a 3x3 matrix. And then it actually becomes harder to find the eigenvalues. Sometimes solving cubic equations and equations of the fourth order, that's something that you would use MATLAB. I do have a MATLAB script that will actually solve. Well, maybe I could do that tomorrow. A MATLAB script that will actually find the eigenvalues for you. Okay. Any questions? Okay, so everyone's aware of the schedule. So tomorrow, once again, my plan tomorrow is to have a very short class. Tomorrow you'll be taking exam 4. Oh, we can go over exam 4. What's on exam 4? Is everybody seeing the blackboard?
Yeah.
Okay. So exam 4. So exam 4, you have to find the Laplace transform for 3 problems. So in other words, it's 15 points. All right. So you have 3 problems, A, B, and C, where you have to find the Laplace transform. Then you have to find the inverse Laplace transform for 3 problems. And then you have to solve an initial value problem that applies the unit step function. Okay, and then find the general solution for a given system of linear differential equations. We have to find the eigenvalues, eigenvectors, and the solution. So once you find, I want you to be able to show me the eigenvalues, show me the eigenvectors, and then write out what the solution is. Exactly what we just did today. And then a spring mass system that applies the Dirac delta function. So this, so both 3 and 5, you have to solve by the method of Laplace transforms. Okay. I thought the ones that I gave you the last time were real simple. Almost everybody got 3 right as far as exam 3, but 4 is where people fell apart. And I was disappointed that you didn't realize that you have to have sine and cosine as the solution, as a general solution. And then when you apply the boundary conditions, or the initial conditions, you're gonna get signed. Okay. All right, well, that's it for today. If anybody has any questions, I'll stay on. And, you know, I wish some people were doing better on the website. It's unfortunate that right now, some people with A's are gonna end up with B's unless they really get going on. And the same thing too, there's a couple of people with B's that end up with C's. Okay. All right, so that's it for today, and I'll see you tomorrow for a short class tomorrow. Or it could be long, depending upon your questions.
I have a question.
Thank you, Professor.
Sure.
You have a great day.
You too. Yes.
How many problems are we gonna have on the final?
I'm not sure yet.
Okay, thank
I'll
you.
talk about that on Wednesday.
Thank you.
Okay, Professor, have a great day.
Okay, you too.